So I want to talk about two things today. I want to talk about research software, and I want to talk about software quality and how we can see them together. Okay, so let's start talking about research software. Okay, so this is a slide that I put together some years ago about what is research computing. So, I come from basically down here. Okay, my first jobs were down in the um, where what kind of IT support, what was called third line support, the system support, and then I got drawn into this world where I was supporting a lab, SANBI, the South African National Bioinformatics Institute, that is over here, and the students were doing this thing, okay, research computing, okay. So what they were doing was they were using computers to do their research, which is now an incredibly common pattern. I mean, I think almost everybody is using computers to facilitate their research in some ways, but in terms of actually using software, when I last checked the figures from around 2018, the estimate was that about 1 in 5 research projects actually produce software as part of the research enterprise. And when they produce that software, then it's typically postgraduates and faculty producing some software for their research projects, and then they that is relying on a domain specific. The domain is bioinformatics tools and libraries. So we might use something like BWA or BioPython or something like that, which in turn relies on broader scientific libraries. A lot of people are using, for instance, Jupyter Hub for their analysis. I use it a lot in my teaching. And of course, we have broader scientific tools, libraries that do matrix algebra and such things, right? And then who's doing this? As I said, postgraduates and faculty. Down at the bottom, we have what I call systems engineers. I prefer this term to systems administrators, although I haven't entirely come up with a term that I feel is easy to understand, because these are people who are building the research computing systems, not just running them. And then ideally in the middle, you've got some research software engineers. But if you look at like the institutional support tends to be well oriented around this side, not so well oriented down here. Okay. And that is echoed in terms of the unseen in research software. So software contributions are not tracked in my country, South Africa, and I don't believe that they are in fact tracked by any of the science councils on the African continent. There is some work in other in Europe and other places to do so. Deployment of public code is typically invisible. So scientific code doesn't typically have customers in the same way that, for instance, your Microsoft Word does, which means that like when I, for instance, make a tool related to something in Mycobacterium tuberculosis, I don't actually get to see who uses it. And very, very often the publication is on the results of the work, not on the software. So you can't track software via publications either. And then as I said, the connection between the software users and the developers is variable. Sometimes we are one community. I know some colleagues in cosmology have been developing some model code as a group, and that the user group and the developer group is very much interlinked. But many of us use software from people that we've never met, and that we have inconsistent feedback mechanisms to reach. Okay, and taking this further, trying to deal with this unseen, we have some data on who actually makes this research software. Okay, it's not, as I said, it's not tracked in its own right, but there have been two key surveys. One by Hane et al. In 2009, that basically did a kind of word of mouth and kind of online survey approach, and one by Pinto et al. In 2018. And I would like to point out that the 2018 survey was done by researchers from the Global South, in fact, from Brazil. So I'm quite happy about that. And both of these looked at how scientists develop scientific software, but the Pinto one particularly focused on the R community. But what it did, instead of just putting a survey out there and hoping that people find it, it went through CRAN and tried to contact the authors of the packages in CRAN. Okay. Um, and what did they find? That research software is mostly created in academia, minorities created in government and other places. It's mostly created by academics with PhDs or in the process of getting their PhDs. So these are more senior academics. Um, However, both surveys show that a substantial minority of software is created by software engineers. I mean, research software, which I think is quite um, encouraging for those of us who've been talking about research software engineers for years and often being not so well understood. But then most of these research software creators are largely self-taught. So they're learning how to code by themselves and maybe a little bit of code education, but mostly without formal education. And within their work environments, they're given limited opportunities for learning about software development. Okay, because they typically are working, as I said, on the kind of faculty level, where professional development is not oriented around things like software development. A few more metrics based on the Pinto research on research software in R. The median package was 1,600 lines of code, which I think you realize is quite a large number of lines of code to keep in your head, right? The creators of research software, and this is interesting given the important role that faculty members spend on creating a research software, spend about 30% of their time creating software. Um, Given the fact that many of these are academics, many other responsibilities, I think that time must be quite pressured time, and then fighting to maintain that space is quite challenging. If you look at what the survey respondents said, most research software creators across the last decade are actually increasing the amount of time that they spend creating software. So we're seeing the importance of research software as research products as part of the research process increasing over time. Okay, it is still being developed either alone or in small, less than 5 people teams. Um, and then coding rather than planning or quality assurance is the most common activity. So typical view of how software fits into to research is the image of somebody opening up their machine and opening up VS Code or something like that and getting going, not sitting in a larger team and doing architecture sessions and for instance. Finally, on who's making this research software, we have a multi-leveled equity gap. About 80% of research software in both of these surveys was being created in the USA and the EU. Now that does track with where um, research funding is most plentiful, but still. Um, About 80% of research software creators are male in both surveys. In fact, slightly more than 80%. And Nelda and I can tell you all about this when trying to organize meetings in the space. Okay. Less than 1% of research software is from African creators. Okay. So again, tracks with the very small part that the African continent plays in the global research publication system and the very small amount of research funding that is available in Africa, including from our own governments, who consistently spend less than 1% of GDP on research and development. However, we had an event, the Research Software Indaba. Click that link when you get the slides to see some highlights of some amazing research software projects from mostly South Africa we were highlighting. So it does exist. And if you are managing scientific computing, please click on that link if you haven't done so already and fill in the Science for Africa Foundation's scientific computing survey that they're running at the moment, which I think will be incredibly useful to make some of the unseen more visible. Okay, so that's research software, where it's coming from, who's doing it, and so on. So then let's look at software quality. Okay, so what is software quality? So this is from a paper by my friend and colleague Colin Venters that looks at software quality in 3 dimensions. Okay, So it's about the product operations. Is it correct, reliable, efficient? Does the software have integrity? Is it usable? Then moving on to the next part of the triangle, can it change? Is it maintainable? Is it flexible? Is it testable? And that's incredibly important for change. You have to know that it's still working after you've changed the code. Okay. And then the transition. Is it portable? Is it reusable? And is it interoperable? Now, I am, as Anelda mentioned, a co-founder of Research Software and System Engineers Africa. At the moment, we cannot efficiently update our website because the template that it depends on has become incompatible with our version of the website. So we are not able to transition the website to a new version. So yeah, and I'm sure many people who create research software have this experience that the dependency changes and it breaks something fundamental in your code. So that's software quality. Okay. So quality is a non-functional requirement. Okay, so this is orthogonal to what the software actually does. Quality factors. Now that's these things here that I've highlighted. These cannot be measured, like reusability, interoperability. These things cannot be measured directly. So therefore, we measure criteria, right? So they stand in for measurements. So code churn, cognitive or cyclometric complexity, lead time for changes, I think is quite important. So, do you kind of get scared when you want to make a change to the code? How long do you have to study the code before you can start writing something new? Um, but the focus on quality criteria can put the cart before the horse. Okay, so the quality factor is your goal. And in fact, what we should be thinking about, the direction that I believe we should be thinking about this thing from, is from the perspective of architecture rather than criteria. Okay. And in this regard, software sustainability is a meta factor of quality. So I've talked about these different factors, and they make this nice triangle. But sustainability is what I call a meta factor. It's an overarching um, a factor that actually relies on those others. And again, this is taken from another paper by Colin. The link is over there. We don't just talk about this thing. We had a workshop last year in July, the first African Sustainable Research Software Engineering workshop that was held at Sanbi. This photo is taken at Sanbi. There's me, there's Anelda, there's Colin and Bridget. So these were the organizers, and all of these organizations. And we will be having something in July this year again. Okay, so there will be a version 2. And getting back to software sustainability as a factor, sustainability is the capacity to, that was meant to say endure, the capacity to endure. Will your software, will your software still be there 5 years from now? And then there's 4 dimensions. There's economic. Do we have funding to continue working on the software, to continue updating it? There's environmental. I mean, we've recently seen a whole lot of controversy, but also a big cancellation in plans to build new data centers that was at least indirectly driven by the resource cost of the so-called AI boom. Okay. And I think that we really are paying far too little attention to the environmental sustainability of our research activity at the moment. Um, I was very distressed reading a African Union NEPAD document that basically focused on buzzwords like blockchain and AI without any consideration for either the appropriateness as technical solutions or the environmental footprint of these technologies. So is it environmentally sustainable? Socially, as I said, the software is being created by very, very small groups. Are they going to endure? Can we build communities around these things? And is it technically sustainable? And technically sustainable has got a lot to do with those quality factors that I mentioned earlier. That it's the easiest thing to actually measure. But even so, it's still not. Remember, don't put the cart before the horse. Okay. So change is key to sustainability. So basically, the way we can best understand whether a research software is sustainable and therefore whether it is good quality is whether it is enduring, and that endurance is related to changeability. Okay, so has it evolved, kept up with the dependency evolution, kept up with the requirements evolution, and the technical debt. Because remember, every piece of code that we write is a liability, right? Because that's something you have to maintain. So the technical debt is visible in slow and fearful changes. I mean, as a developer, I'm very familiar with, being scared to actually change something in case I break something else. Okay. Um, the change is often external, the changing software or the social or the functional ecosystem. And architecture, which at the moment we don't have very good criteria for measuring. Architecture is key to evolvability. So we really need to do a better job on that level. Okay. So where to from here? Research software creators they need architecture patterns. They need boilerplates. So we've looked at certain kind of cookie cutters in my work, cookie cutter projects, boilerplates that help them structure a project well. They need metrics that speak to their needs. As I said, metrics that speak to quality factors, but also the overarching architecture factors. And they need opportunities to learn beyond just coding, and they need recognition on a continental scale. So I'm very glad to see somebody from Science for Africa Foundation who's got that continental vision here, but we really need the recognition to be in the AU documents, in the OECD documents, in the UNESCO documents, and so on. And yeah, so that's me. Thank you very much for listening. I would love to thank my what I call my co-thinkers. That's Anelda, that's Colin, that's Birgit, and the four of us have been working together on thinking through these things, and I could not have done the presentation without them. And there's my email address. So I will leave it there.
So, as Anela said, I'm from the South African Astronomical Observatory, which is one of the national facilities of the National Research Foundation of South Africa. And at the observatory, we operate more than about 25 telescopes. So these are based about 350 kilometers away from Cape Town, out in the Karoo, where we have clear, dark skies. Um, so over the next few minutes, I'm going to explain to you why software matters at the observatory, in particular software quality. And perhaps as well, you'll realize that our software is so important that it may even one day tell us how life on Earth is going to come to an end. So to dig straight in, to give you an idea of the variety of software we have, I'll just focus, if you look at the bottom, this is a panoramic view of all the telescopes that we maintain and operate. Many of them are in partnership with international institutes, but I'll just focus on three of our workhorse telescopes. So all three of these telescopes are completely under software control, and all the software that operates these telescopes is designed, developed, and in-house. And in addition to the telescopes, each of these telescopes has a variety of instruments on the back ends. So including spectrographs, polarimeters, imagers, and we specialize in high-speed imagers as well. So, and most of these instruments are also developed in-house. So that includes their mechanics, their optics, their electronics, and then of course their software. So the software has to be able to operate the instruments, configure them, and then and obtain images or spectroscopy from them. And in addition to that, we then also develop the software tools in order to calibrate the data and for the scientists to analyze the data. So as I said, all three of these telescopes are completely under software control. So that allows them to be operated in three different modes. You can either go to Sutherland and sit in the control room in Sutherland in front of the control monitor and control them from there. As of a few years ago, all three of these telescopes can now be remotely operated from anywhere in the world. So we developed the software services to allow remote operability. And then our most advanced telescope, this one in the middle, we've upgraded to be completely fully robotic. So this telescope operates on its own at nighttime without any influence whatsoever. So moving on, so this is just, we won't go through this list, this just summarizes what I just said, but a couple of other things to add. So on top of all the software that I've just described, we have to create an interface for users to manage their programs. This is usually through a web interface. We've developed queue schedulers, so particularly for that fully autonomous telescope, it has to balance priorities and making decisions on which observations to do next. We've developed databases, science databases so all the data that comes from all those telescopes is put into a fully searchable database, which we make available through a web front end. So all users can search the database and retrieve the data. So basically that means that the observatory, we have a layered ecosystem of research software that spans from telescope operations, instrument control, calibration pipelines, all the way to scientific analysis software. So just give you a couple of examples of the sort of science we do with the software. So it's our software actually that enables our telescopes to be flexible and in particular at the moment be capable of rapid follow-up. So it's rapid follow-up that's the key thing in the international astronomy arena at the moment. So for example, this lower plot here is a spectrum of a supernova. So supernova are being detected all over the world all the time. But a crucial next step with supernova is identifying the type of supernova. And for that, you need spectroscopy. So our robotic telescope can quickly follow up supernova, create the spectrum, and then quickly identify the type of supernova. And some of our users want immediate feedback on their observations as soon as they have made. So we've developed software that has a web front end. So as soon as data has been made, we've flux and wavelength calibrated and make those observations available within 1 minute of the data being obtained. And another example of one of our niche areas is high-speed photometry. So this is another recent discovery where we discovered an object that varies rapidly in time. So you see this is a time axis and brightness. You can see these very rapid pulses in brightness from one of these objects. So because we now have a fully robotic telescope, this means that this telescope can talk, if you like, to other telescopes around the world. And one example project is that this telescope is always listening to, there's another network of telescopes run by NASA. It's called the Atlas telescopes. They have about 3 of them around the world. We host one at the observatory. And this Atlas telescopes, they monitor the skies for new objects, basically near-Earth objects. So these are the sort of objects that might one day cause danger for us on Earth. So even though the Atlas telescope can discover them, it then requires more detailed follow-up observations in order to calculate their trajectories. And this is what our robotic Lasady telescope does. But to do this most efficiently, we've removed the human entirely from this sequence. So the NASA Survey telescope automatically detects new objects. That telescope then sends an observation request via an API to our Lasady robotic telescope. It gets inserted into that queue. This telescope then does the follow-up observations and calculates the trajectories. So for example, in 2023 alone, we responded to 145 triggers of potential new near-Earth objects from the Atlas telescope, and 71 of them were then officially recognized as near-Earth objects. So one day, perhaps, it will be the software on not this telescope that will tell us if any of these near-Earth objects would result in end of life on Earth. So this is another fun example. Our telescopes can also track satellites. So I'm sure you've heard that I've heard about the Artemis mission around the moon last weekend. So this is a movie sequence of, you can see, if you see my arrow there, you can see that dot going past the screen. So this is the Artemis satellite spacecraft on the way to the moon. And from our perspective in South Africa, it just so happened to pass in front of this well-known globular cluster. So this got us a lot of media attention a few days ago. So why does software quality matter at an observatory? So I think you'll now realize in astronomy operations, it's not just the research output. Software is part of the whole chain, from instrument, the workflow, all the value chain for every observation. So here, a simple test for quality at the observatory is 3 questions. Can we trust the software to operate scientific infrastructure? Can we trust it to make decisions in real time? And will it be maintainable a year from now? So in terms of reliability, our systems must work at night under operational pressure. Because it's scientific data, it must be reproducible, it must be traceable and reviewable, and it must be sustainable. So the observatory has been here for several decades, so I should mention that we have a lot of legacy software and hardware. So there's quite a mixture of new modern software and legacy software working together. And so, but now the big thing that's on our minds and everyone's minds, of course, is AI. And how do we maintain human oversight now that AI is starting to make an impact on our operations? So to finish off, I just introduced a project we're calling the Intelligent Observatory. So this is where we're starting to use AI technologies into making our observatory more intelligent. How we're using AI in operations and in science. So I'll just give you one example of each. So the observatory has been around for over 200 years, actually. And in that time, we've never had a document configuration management system. So all of our documents basically looks like this image here, right? We have information buried in reports, software documents, technical documents, you name it. It's a massive information resource, but we've no idea how to extract information from it. So the question is, can we use AI and technologies like RAG, retrieval augmented generation? Can we just throw all our documents at that and create an intelligent interface to the observatory's information? And the other example is our telemetry project. So have you seen, we have a vast amount of telescopes and instruments, a lot of software services running them. They're all given telemetry data, which we put on dashboards and we put into databases, but we don't have anyone who's looking at the databases, and we don't have anyone who's watching the dashboards. So how can we use AI to do that work for us? How can we use things like agents and maybe things like OpenClaw? How can new technologies like that help us with all this all these issues we're trying to resolve? So some final thoughts in terms of the research software enterprise. How can we, I guess, get better recognition for the research software engineering work we do at the institutes? How can we have more cross-site learning between the software teams and the domain scientists? I should have mentioned that our software team is about 5 people. Half of us are scientists and half of us are professional software developers. And then moving forward, how can we get some more practical guidance on how we can trust AI, particularly in our environment of live scientific operations? Great. I think I'll stop there. Thanks for listening.
My perspective will be quite practical. We're a civic tech organization based in Cape Town, but we're largely an open source and open first organization. So I think some of my insights are quite pragmatic and quite focused at the organizational level, but we do tend to create and build software very much in a co-creation context. You know what I mean? As an external partner, partnering with different organizations in terms of their software, though obviously we've built some stuff internally. So I think that perspective might be useful. And I think it's also worthwhile thinking about that in our context, we often work in environments where what constitutes data quality and data standards isn't really defined, and so that impacts the context in which we're working. We're also working a lot with community groups and governments as well, co-creators or clients or partners. And so that's the context. But we develop largely in South Africa and in the region. And that's a particular digital context, I think, that's worth thinking about. In the context in which we work, the fundamental context is that, there's a low investment into digital, both digital infrastructure and digital products across our clients group. And that includes both government and civil society groups and civil society actors. Some of that is because of resource constraints, and a lot of that is also just because of organizational cultures, I think, which are not, where innovation and technology are seen as an add-on to different functions. But also, I think, speaks to a bigger economic reality of, Mazzucato, that great economist, talks about, how in the sort of late stage capitalism we're in, there's a very low reinvestment into R&D from companies and organizations generally. And I think we see that definitely in our context. So I think a lot of those sort of supply side challenges are fairly universal. But, certainly within South Africa, and the region, the realities of digital inequality and data inequality are very, very real. So that includes, the fact that we still don't have universal access to internet. In a lot of countries, electricity provision is very patchy. Data is very expensive. That's a very generalized statement, but you can say that on the African continent, data here is expensive. And I feel very comfortable making that uniform statement. And so that impacts both how you have to build technologies, but it also impacts the realities of how the people who are going to use those technologies, the context in which they're having to work. And that impacts, those limitations also impact people's digital capacities, right? Because if you have a limited experience of being online, how you're online and how you engage once you're online is very different. Next slide, please. So what this means, how we've generally approached the building of technologies and civic technologies in order to deal with this context is by heavily centering user-centered design and user analysis in our processes. And when I talk about that, I talk about doing that at scale. So for our one project, Vula Kamali, which was developing the South African government's open budget portal, we did engagements with about 1,100 people across the country. It's not meant to be a representative sample, right? It's not research, but user research is about learning as much as you can about your audience in inevitably, so you create something that's worthwhile. And generally, we have to do two streams of user research, one which is dealing with front-end users and one which is dealing with back-end users, because the context in which we work, generally people are creating products that they will need to manage, but that are trying to meet the needs of external public-facing users or whatever. So there's always that to consider within our user analysis. We obviously design for a data scarce and erratic context. So, most of our products are designed to work offline, designed to be responsive on cell phone technologies and all those kinds of things. And those things matter in any deploying environment, I think, which includes the research software environment. In terms of how we design, but this is largely because of our civic context, we look for augmented participation, which is that we never, because we're working in a context in which sort of the civic or the political is very important, and trust is very important, we try not to eradicate human engagement. But that's the context, right? We're talking about civic activism and those kinds of things. So it's a different context. But we obviously measure for effectiveness, and while that might seem very trite to this audience, you'd be surprised how much the design and deployment of technologies in the sort of more like political spaces and civic spaces doesn't actually have any, consistent measuring of how effective the technologies that are being deployed are in their context, and whether they're actually doing what it is they're meant to do. I mean, that bothers me on many levels, but it's, you think about proportionality, like, why are we investing? Are we getting the outcomes we need by deploying this? And is it worth the risks? I really enjoyed Peter's sentence. I even shared it to my team online about every line of code is a liability. and everybody agreed, Peter. There were lots of thumbs up on our Slack channel. So that was fun. But yeah, just that we obviously, because of the context, participation is very important. But I think even when you're developing software in an organizational context, that participation or organization-wide is very important too. And then obviously we lead with open, and we see open source technologies and open data as a way of both avoiding vendor locking and improving the potential for long-term sustainability of any product. Next slide, please. So when I was thinking about what to add about what we've learned, I thought it might be useful to focus more at the sort of organizational level of what some of the challenges in developing software in these contexts have been. As I've mentioned before, obviously financial resourcing is often a challenge, and technology is viewed as an expense and not an investment. And linked to that, I think, is the sustainability challenge, in the sense that when you are looking at developing technology and it's considered an expense, there's seldom a plan for the long-term sustainability, and either in terms of internal resourcing, but also financial resourcing in order to maintain products and keep them up to scratch and up to form. And you will see that deficiency even in the project or the initial project design, where you seldom see time or investment placed in, say, handover or the longer term onboarding of these products. And there are ways you can account for that properly in a budget, but that's a plan that is often lacking. There's obviously a skills challenge in having the internal team members available to either further develop or maintain technologies, although, obviously in your context, that's probably less so. But what is interesting is what we've seen is those capacity issues impact how people procure for technologies, which is something I don't think we've discussed enough. And I think you can meet that gap quite easily. But that's something to think about, when you're insourcing technology as well, or development or partnerships, that there is a degree of capacity that is needed in order to design well for that and productively for that, which includes appreciations of like agile development context and those kinds of things. Although I won't give you the speeches on agile development, I will leave that to my very annoying team to do in another context. What we have seen as well, and I think this is very fundamental for us, is that often what people think is a technology problem is actually a data problem at an organizational level, and that a lot of people get a lot of productive benefit from first focusing on improving their data governance practices organizationally, but also that you need those data governance foundations in place to get a productive value out of software. And I think that's often quite overlooked, and it's incredibly important to our philosophy of software development. Just in terms of the trust gap, I think when you don't involve the people who are internally who are going to use this technology enough, it's very difficult to overcome a lot of the behavioral gaps, but it's also a trust and buy-in issue, right? I think often senior people think that you can tell people what software they have to use. And I think behaviorally people find interesting ways to resist that, even when they're not express about it. People protest very subtly. And one of the ways they do that is in terms of the uptake of software and technologies in their everyday practice. So I think that trust gap is very important. Next slide, please, which I think is my final slide, if I calculated right. So what do we see, as the kind of opportunities from this? We obviously very fundamentally believe in open source software and open data. One thing to note on open source software is often the documentation is terrible. And often, you're relying on communities, who are very collaborative, but who disappear, But what it does allow you to do is have very low cost prototypes. And that is, a great way to test an idea. And so I think there's incredible value in deploying open source, particularly in prototyping. And I think local collaboration helps when you're looking for people who partner with, so that because they already understand the context, and particularly in South Africa and outside South Africa as well, we have internet penetration rates which aren't uniform, but we're also dealing with partner regional countries which have internet penetration rates at like 60%, so we're dealing with very different digital contexts. And so local collaboration is really, really important. I think picking custodians, and I think we were actually the previous speaker, Stephen, you were talking a little bit about this as well. Picking custodians that have domain knowledge is really important, and I think is an important part of embedding those technologies within the organization. I think sometimes the domain specialization is more important than the technology capacity or digital capacity, because they become better champions for that software because they care so much about, the outcome that software is meant to be introducing to their domain. And then for us, as always, the primary investments for us is data governance and internal data governance systems, and building something that works. And we believe that's the foundation for better software generally, and across organizations and spheres of specialization. So next slide, but I think you see, look how concise I am. That's us, and anybody can follow up with me if they would like, but I'll stay for questions. See, thank you.
My talk is called It's All Code. And the reason why I wanted to talk about this, because I previously worked in an institution that wasn't research, and we used to follow lots of processes. But I just wrote the code and followed the processes. I really didn't investigate as into why I should follow these processes. But when I got to the SKA and SARAO, I started to see that we all write code, and sometimes we might think that if we don't have these fancy processes, our code means nothing. And I saw that at the SKA, there was purpose behind the process. So I want to talk about the purpose that actually allows you to build these elaborate processes that allows your code to then go and be processed into different means and for different use cases. So let me just get started. So the first statement I'd like to just say is that we've all, or many of us have written code that works, but sometimes we've written code that works, but it really does not matter. And what we're trying to do at the SKO and specifically in my team, which is called Team Korir, and I guess in any meaning software system, we're trying to write code that has a purpose. And it should never be an afterthought. It needs to be the starting point, because if you don't have purpose, you won't know how to follow through. And at the SKA, we are trying to achieve something that's really big. We're trying to achieve something that's never been done before. We're trying to build the world's largest radio telescope, and it's a collection of governments working together in order to build this massive thing that is supposed to contribute towards scientific discovery, and it's supposed to aid us as human beings, to better understand our world, to better understand our past, so we can understand our future. And so there's a lot of coordination going around. There's also a lot of data processing. And we're trying to do this thing, and it's amazing. And because we understand we're trying to do this amazing thing, we have purpose, and we then have built on that, on those pillars. And so what I want you to take away from the statement is that just that when you have a complex system, you can't afford to build without purpose, because when you have a big project such as the SKO, misalignment can trickle in very quickly. And misalignment is not just, oh, okay, we need to do this again and over the next 3 months. It also means us wasting taxpayers' money, and we don't want to waste taxpayers' money. So we need to do things correctly, and we need to do things efficiently when we plan to do the work. And the next slide, I just wanted to summarize what I believe purpose is. So purpose tells you what you want to build, but it also tells you what you don't want to build. For instance, you might just want to build a simple dashboard that shows you the temperature of a certain place in the world. And then all of a sudden now you start adding in different functionality to this dashboard that does not need to be there. And it wastes time, which then elongates the project and also doesn't give you a clear definition of where to end. And so you also need to know, when you have purpose, how to measure this purpose, how to measure that it's actually successful at the end of the day. Because as I mentioned with the previous thing, if you don't know where to stop, your product will never get to market. And then you're building for forever, and you might miss that window of opportunity that you need to have in order to actually display what you've made. And so I've just put together a small train of what I think gets you to these fancy processes where you are sending your code through different pipelines and it's processing things. It starts with purpose. Then we get to the requirements. We then are able to design correctly. Then we code. We don't just code at the beginning. And then from the code, depending on what you're coding, you then can then build on and see, okay, maybe I need a distributed system. Maybe I need cloud, or maybe I need a very rigorous testing system. Okay, let me try and set up pipelines on GitLab that I can test this code very rigorously. But you'll never know that if you don't have the other components leading up to it. And so another key point, or key points rather, is that processes are never the starting point. Code is also not the starting point. Purpose is the starting point. And you'll probably hear me mentioning purpose a lot by the end of this. If you just take away that one word, it will be sufficient. And I just wanted to also speak about briefly how purpose shapes the software the software processes that come after you've actually coded. So within the SKO, we have very distributed systems. but they also need to be very modular because we scale a lot, and the software needs to be able to be deployed in different environments. So the way we write code, we have to think about that consistently. We can't write things that can't use certain technologies. We have to have a very wide view of what we're doing before we write, and our architecture then is then built from that point of view. And then we also have very rigorous testing and quality standards because we're trying to produce results that scientists will one day use. We have to make sure that it's very accurate and that what we're reporting to the scientists is actually true. So we need to set up those things within our pipelines. We've got things like unit tests and acceptance tests, and then we've got another level of testing. We call them L2 or L3 requirements, but it's more of a system engineering level of testing before we take it to site where we can test on the actual hardware. And so there's a high cost to failure. So we want to test as many things before it gets to site so that we can rectify anything. Another thing is the way we communicate and the interfaces that we use. Because we interface with many teams, my team pours into another team. It's almost like we have buckets and we're continually pouring into the next team. And we have to have very clear APIs for collaboration. And we also need to have documentation within the code and also read the docs where people, so basically our code is open source, so anyone can read how our software works. But also the teams that need to use our software need to know how the software runs. So everything has to be very clear. It's very precise. I probably will speak about that a little bit more on the next slide. The last point here is about integration and scaled agile. At the SKA, we use the SAFE framework, which is scaled agile. We do this because we're very big and we've got many teams. And the way that we work is we plan work for 3 months that we believe we are going to achieve. And then we get together after the 3 months, we assess where we are, and then we plan again for the next 3 months. And that just keeps us in a good cadence to see that we're on route to finishing the goals, because we have certain key points within the timeline of this project that need to be met. And so the processes that you can see that I've mentioned that we have, some of them, they're not arbitrary, but they're more of a response to the purpose that we have set ourselves up in the beginning. And just going beyond the SKO and speaking more towards, I guess, research and anything else, personal projects or startups or even internal tools that you make to expedite certain processes. All of these things require purpose. You don't just start building not knowing why you're doing something. And when I wanted to just contrast the two different things, if you are purpose-driven, your code is more focused, it's more maintainable, and it's more impactful. But if you're process-driven, your code might tend to be bloated and misaligned and unused. And you might find that when new people come onto your team, you find that they will look at certain modules and see that certain functions are not used within your code base, and that can confuse people. And so dead code is one thing that you want to get rid of, and you don't want to just have things just because you can. And so one thing I also want to mention is that process-driven code will probably work. It probably will work. It'll probably solve whatever issue you're dealing with. But it probably just won't be as efficient as purpose-driven code. So it will get the job done at the end of the day, but depends what your end goal is. And another thing I just want to mention before I close is that before I write code specifically and within our team, we always ask, why does this need to exist? So if you get told to move a certain bit of code into another module and you just do that, you copy paste, you move it, your job is done. But if you don't understand why you're doing it, you'll never understand when it breaks how to fix it. And you won't actually know how to extend it or even how to make it better. So you really need to ask yourself, why am I trying to move things here and there? And if I don't have a reason, don't do it. And another thing is that your processes will naturally just scale as you give your code more purpose. Because, for instance, sometimes we just want things to be complex. We might tend to want to use threaded programming instead of just using normal single-threaded programming, because you think that, you know, making something more complex is more better. So you need to understand why you're doing something at the end of the day, and really just write code that matters and that's usable and that's maintainable for the future. So yeah, this is just what I wanted to mention about the work that I do within the SKO and developing software for local monitoring and control of the telescopes. Thank you.
It's a pleasure to be part of this conversation. The title of my talk is Elevating Usability, and I hope by the end of this presentation, it shall be very clear what I'm trying to communicate, that usability really needs to come as a first-class design requirement. So in order for us to motivate this story, I want to tell you a story. It's a story about a man called Ivan Sutherland. I don't know if anyone here has heard of Ivan Sutherland. Ivan Sutherland he studied electrical engineering in the 60s, and then he did a PhD at MIT, and he developed something called Sketchpad. Now, Sketchpad at the time, if you can think about the kind of computers they had at that time, they were very primitive and simple. These were computers that needed to be programmed using punch cards like you see over there. And if I move a bit to the side, there's a QR code. You can actually find it on my slides, which are on the website. That video shows you how Sketchpad worked. Now, what Ivan did was he put together whatever technology was at the time, and he developed a means of drawing on a screen using a light pen. A light pen was almost similar to what we'd call a stylus right now, but it used light to sort of communicate between the screen and the device to capture the position where the user was pointing. Unfortunately, it wasn't a very useful technology because it would cause people's hands to actually get cold, given that if you're holding it upwards, the blood doesn't flow towards the fingers. Anyway, so what he did was he came up with a system called constraints, and he would give instruction to the computer. He would draw two lines, and you just tell them, you know, make yourselves perpendicular, and the lines would be perpendicular. And this became a very powerful way that you people could draw on the screen. Now, the idea of approaching it this way was really instrumental. And underneath whatever he developed, there are a couple of technologies which have come to be so influential. And I'm going to show you what these were towards the end. But number one was he pioneered computer graphics. This was really the early days of computer graphics. And then within his program, he designed ways that you could have elements of code that could be copied about, that could share behavior across one another, so that you could make changes in one part and it would propagate across. And that's what we now think of as object-oriented programming. And then the third thing is his application of the light pen, this UX, this very good experience that he provided for users. But there's an uncomfortable contrast between how he did things and how we do things today. So like now fields like design and engineering have moved into a more interactive and a more constraint-driven approach. A lot of scientific software is still written in terms of scripts and in terms of batch jobs and in terms of tuning parameters and pipelines. And what I really want to do is, by the end of this talk, is really to try and capture your imagination of what is possible when you make usability a first-class requirement. So I'm going to give you 3 case studies. I'm going to start off with one which has really transformed a lot of the work that's there in structural biology. So this tool called RelyOn was developed by a guy called Charles Scherez, who's based at MRC in Cambridge. And you can see by the number of citations, it has 6,100. Actually, when I took this screenshot, there were 6,184. The next time I took a screenshot, when I did a search on the page, there was 6,185. Like literally, this is how many citations this software is getting, how used it is. And then later on, they developed some new tools, they added some new functionality, and that again has almost 5,000 citations. And this tool was really instrumental in bringing about a big transformation. Now, it's just one component, the software side. There was also technological advances that happened at about the same time, things called direct electron detectors that revolutionized by introducing very high resolution images to allow structures like what you see right behind me here. Atomic level resolution using a tool like Relion. And this is the kind of transformation that I think can actually come about. So this is one example, our first case study. The second case study is, some of you may know about this, it's a tool called Galaxy. So Galaxy is a tool that you use on a web browser, and I see Peter is giving a love heart for that. It takes a lot of the bioinformatics tools on the diagram that you see here on the left of the screen. There are hundreds of tools that are available for genomics analysis across all the different things you can do, whether it's doing assembly or mapping or reconstruction or quantification or comparison. There are hundreds of tools. The beautiful thing about genomics is they don't squabble about standards. The standards are very well defined, which has allowed this ecosystem of tools to develop. The unfortunate thing is most of them require you to work on the Linux terminal. So in addition to learning about Linux, learning how to work on the terminal, you then learn about these tools, which can be a bit of a steep learning curve. And what Galaxy did was they created a web interface that could integrate all these tools together and allow users to just explore the data and do a lot of the complex heavy lifting behind the scenes. So this is our second case study, which I think is really an exemplar. Now, Relion and Galaxy are open source projects, but I don't think it would be wrong for us to also consider some of the proprietary tools that are available. And I think there's a reason for this. So within numerical simulation, there are tools used for computational fluid dynamics, for finite element analysis, and all sorts of multi-physics modeling. And I'm sure these are some of the tools you also use, Barbara, in the work that you do. And these have been developed by companies which charge an arm and a leg for their license fee. So for example, ANSYS, COMSOL, Dassault Systems, Siemens also have their own tools. There are a couple of open source tools, but they don't quite compete at the same level. And you can tell this by the license fees that are charged. So for example, if you get one of these tools, just a basic tool costs about $5,000. And then there are individual modules that go upwards from $20,000 to even $100,000, because some of these tools are used within oil and gas industry, within manufacturing industry. And a lot of these tools they're CPU locked or they're user locked. So that means only one person, when you pay that $20,000 license fee, you're only paying for a single individual. And that's research licenses are more affordable. They are $1,500. And for students, they are free. And of course, we know why they're free. They want the young trainees to start off with these tools as the de facto standard, so that by the time they're in industry, this is what they rely on. But the key point of this slide is to illustrate that there is great value in software. I could have given many, many more examples, but just what these three examples really illustrate. So what does this actually mean in terms of how we do software? And I want to sort of bring this to a close by thinking about three key things that I think we should do when it comes to software. So number one, unmistakably, is I think we need to treat usability as first class. And I'm going to show you how we can actually do that and how we can leverage on some of the new technologies that have emerged. So number one is think about all the different interfaces by which users interact with software. Fun fact, I wrote a Mozilla plugin in 24 hours, and I published it to the Mozilla website, and I got it approved just this morning. I've never written a plugin before. But just the fact that there are these other interfaces, using AI makes this so accessible. So have you ever thought of writing scientific software that uses Mozilla plugins, or that uses Facebook plugins, or that uses all sorts of interfaces that are not traditional within software? I think it's really important, and I find I really enjoy the experience of some of the tools that you find within the Mac, that they are really economized. They try to declutter as much as possible and really highlight the key use cases. And the standard example I like to use is Preview. That's used for viewing PDFs. It's such a smooth experience, but it's got very few buttons. If you want to get them, they're there, but they're hidden. And that makes it less intimidating for users to interact with your tools. The second thing, which I think is very important, and I read this from a book on the Toyota production system. There's a phrase they use called Genchi Gembutsu, and it says, go and see for yourself. And what that means, there's and some other people call it technology anthropology. You need to learn to live with the natives. You need to learn to visit with the users who are going to write, who are going to explore your software and apply your software. And two ways to actually do this is really inhabit the world of the user. What do your users experience? What do they struggle with that it's easy to take for granted? People who write software tend to have a skill at abstracting and thinking away complexity. But most lay users or users who are domain invested will not have that skill as developed as yourselves. And therefore, it might be useful to spend time with them. A lovely example I love to give is about accounting. Accountants don't write software, and yet there is great accounting software that's out there. What does that mean? It means that some software developers actually entered that world, understood what the challenges and the pains of these users had, and then elevate outcomes through standardization. And for a lot of new people into software, what they tend to do is they start writing their own standards, their own file formats, and ignoring what's already available. And a lot of effort has been invested into putting together standards, standard protocols, standard interfaces, standard file formats. That really helps the user. And this is one of the things that has worked very well in genomics. There's not been any committee, but because a lot of software developers in computational biology and genomics, they sort of rally around the file formats that they find, makes it very easy then later on to compare how do future tools compare against previous tools. And then the third thing I think which is so important is to invest in design skills. Design skills are unbelievably impactful. I read the biography of John Ive and his story about how he was involved in Apple and how he was brought in by Steve Jobs, and he was involved, and how the amount of effort they would put into just experiencing a product before it becomes released, before it even goes into production, the number of prototypes they would make, the number of trials, the number of people who would be involved in just feeling through a technology. I think that's so important. Visual design has become a primary skill. A lot of users will be put off by something that doesn't look presentable, doesn't look nice. In fact, in the user experience design, aesthetics is actually a trick to try and give users the impression that something is actually easier to use than it might actually be. And then fast feedback. We're now in a day and age where it's easy to very quickly validate tools and experience what they are like before you actually write the code. Do a lot of prototyping, dirty code, experiment with AI. And that's going to be my next major point. So I have a conceptual framework here that I want to present. Traditionally, software has been that we spend very little time doing user research, very little time doing design, and most of the time doing coding. And then we struggle with deployment and making a release. And then finally, there will be some support, which is why you have this faded thing here. So this goes into the future. But then we've had some technologies like cloud computing, which has allowed us to do things like DevOps. So what that has meant is, okay, then now we're going to use things like Docker and Singularity or Aptainer. And that's going to make it easier for us to sort of have a much easier deployment experience, a much better user experience. But it's not quite what it is. The code is still dominant in the whole experience. But now we are in a day and age where we have AI, generative AI. And what generative AI I would like to offer is that it allows us the flexibility to spend more time with the users, understand the users, become anthropologists and inhabit that world of the users. And then try and iterate on design and really explore what that is. Because a lot of the heavy lifting has been done by AI. We don't have to spend that much time. I recently built a project, I think, again, another 24 hours, very quickly, and it showed me how to deploy it so easily that it cost me almost nothing. It gave me all the instructions, and I deployed it in a flash. Now I do a push, and then I do a pull, and I tell it what hash to use. It'll build that the release, and within a few seconds, it's restarted everything, and the new code has been deployed. So Gen AI, I think we should be very bold about using Gen AI to sort of speed up the quality of work. It gives us back the time to spend time with the users and do design. So here's a postscript. I want to end with this. So I told you about Ivan Sutherfield and his invention of the sketchpad. But what I didn't tell you is the whole genealogy of Ivan Sutherfield. It turns out that he was the student of Claude Shannon, who was behind information theory. So he had a really good teacher to begin with. But in terms of his students, he had a student called Jim Clark. If you know anything about Jim Clark was a guy who started Silicon Graphics. Silicon Graphics was a company that made a lot of 3D libraries, one of which was OpenAI. Sorry, not OpenAI, it's called Open Inventor. Open Inventor is used in some tools like Amira and Aviso, which are for 3D image manipulation. It was eventually sold off, but that was one of his students. If you've heard of Alan Kay was the guy, he worked at Xerox PARC, and he was one of the originators of object-oriented programming. He developed a language called Smalltalk, which was one of the first languages to actually use object-oriented programming. And then another one of his students was Edwin Cartmull. I don't know if you know this, but you probably enjoyed some of the work he's done, which has been in Pixar. And then another one of his students was John Warnock, who actually started the company Adobe. And then if you notice, there's a theme here. There's a gentleman by the name of Steve Jobs who took a lot of these technologies. This is what I mean when I say there's explosive potential in usability. These guys invested a lot of effort and energy in making sure that software is of another class, inviting the users to actually think and use technology as an extension of their thinking ability. Thank you very much.
Welcome to the second part of the event today about research software quality across continents. In the next hour or so, we'll be going through some of the outputs of the EVERSE project. So I'll start by doing the introduction. As I mentioned in the previous session, my name is Fotis Psomopoulos. I am at the Institute of Applied Biosciences at CERTH, and I'm coordinating the EVERSE project together with BSc from Spain. So I'll start with some fundamental aspects around research software, which are the FAIR principles as they pertain to research software. So these are the FAIR principles as released a decade ago. I'm not sure about the month, but it's definitely a decade ago now. I quite like this diagram because it's produced by Turing Way, and it highlights how the different elements kind of fit together in the overarching ecosystem. But when I'm talking about FAIR, which is about findable, accessible, durable, reusable, one of the more common questions that pop up along the way is, why should anyone care about FAIR in the first place? And usually people start listening in more closely when we're talking about resources and how they have an impact on resources. So this was an activity that was done, again, quite some time ago, not a decade, but close to that, in Europe, where they tried to assess what is the minimal true cost of not having FAIR research data. In practice, what they realized is that the actual cost is about 10 billion, and this is roughly almost 80% of the entire Horizon 2020 budget, or equivalent of 400% of what the ERC and the infrastructures receive combined, which is a huge number of resources. So with that in mind, one can get an understanding of why talking about FAIR for research software is quite important. But of course, when this was designed, initially it was aimed at all research objects, but in practice, a lot of those things were applied direct to data. So that's why the text in the principle text talk about metadata, which is shorthand for metadata and data. And ultimately, a lot of them were interpreted directly to apply to datasets. But if we start considering what this feels beyond data, in other words, non-data objects, we need to figure out how this can be applied. And this is where this whole discussion about applying FAIR principle for research software popped up, with an effort starting within RDA for a few years, leading to a very well-defined set of the FAIR principles for research software. Already, a lot of those were in place and defined across different communities, like the one in the French National Committee for Open Science in 2019, as well as in the FAIR Practice Task Force in the European Open Science Cloud, EOSC, in 2020. But all of those connections essentially going back to a very fundamental question. Even if we talk about FIRST software, even if we talk about open science in research software, one of the first activities is that we know to pursue reproducibility. This is one of the key challenges. But as it appears, reproducibility relies a lot on how we define quality and sustainability of the software that is involved. And that is one of the main reasons where EVERSE came to be. Essentially, EVERSE is an EOS project, a European Open Science Cloud project funded in Europe. And the main concept is to empower research software as a first-class citizen in science. Of course, as you can see, it exists in various parts of the life cycle. Even if we say that we start with research data, the research software is basically the next step. Even if you collect the data, you need somehow to process them. So it's a very fundamental part of the life cycle. But at the same time, not all software has the same level of reach, of impact, if you want to call it that way. We're talking about analysis code, which is extremely abundant. Everyone is producing code for their own use. But at the same time, this is code that a person or a group is developing for their own use. So they are the actual user of their software. If we start trying to be a bit more constrained in the requirements and how this can be processed, we're leading to prototype tools, essentially software that is developed by a group, but is being extensively used by others, by other groups. The easiest example of those cases are the software libraries, pieces of software that are being used by others to do their own analysis, etc. So we're talking about prototype tools. Less abundant, of course, compared to analysis code, but at the same time, it has a bit more impact and more expectations. If someone is picking up someone else's code, they have expectations on documentation, on how well it's structured, how efficient, they don't have any bugs, hopefully, etc. And then you have the research software infrastructure at the top tier. Significantly less abundant, but also significantly more impactful in the wider community, because this is software that is so fundamental that anyone relies on that. Talk about research software infrastructures. The easiest example I use in this case is Jupyter, which provides a more fundamental infrastructure where other people running their own code on top. So where does this fit? So if you start looking at how we can organize the information that is around there, we're talking about the software infrastructure, the software communities, but these are needs to be coupled also with the software itself, and also the policies, the recommendations, and all the activities that are happening at a global level. So what EVERSE is trying to do is trying to pull all those things together. The scientific software represented by a lot by the different communities in Europe, the science clusters under EOS. The software infrastructure, we're talking about fundamental software like Bioconductor or libraries like PyTorch and how these can be used. The software communities, of course, we're talking about Science for Africa Foundation, RISA, the research software engineering communities, SSI, these are just to name a few. And if you go for science policy, these are all the different high-level policy-making institutions that actually have direct impact of how research software is supported at the very end. And this is where EVERSE comes in, essentially trying to bridge between the very structured way that software is being developed into a more organized way that this software excellence, software good practices are put together, are collected in a way that is useful by the research communities. Essentially, we've been trying over the last 2 years, and I think quite well succeeded in doing that, to collect this information across different domains, make them as coherent as structured as possible, and make them back available into the wider community. We are now in our year 3. We have 12 more months ahead of us, and it's comprised of a wide range of organizations across Europe. And I'm really thankful for all their efforts and contributions making this happen. So beyond the actual scope of EVERSE, what we do need to have is our pilot project, our affiliate project, if you like. Essentially flagship efforts that are already running under the various domains. And you see here the 5 different domains that are very active in EVERSE. And each of them, the goal or the intention is to pick up the good practices, the quality indicators, the services, the activities that are happening within EVERSE, trying to see how they are used in their own context and provide either feedback or directly adopt them as they are, overall improving the way that research software is developed and its own quality along the way. I'm not going to go into the actual outputs. There are more capable people from EVERSE in the call that will be going through them. Essentially, there are 7 major outcomes of EVERSE: the network itself, the RSQKit, TechRadar, the quality pipelines, Dashverse, training efforts that were also mentioned in our first session, and of course, how we can define a formal recognition system to acknowledge all the efforts that research software building requires. With that, I need to thank everyone in the EVERSE community that making this a really impressive output so far. And with that, I will, so these are some few links. I'm sure we'll share them at the end of the session as well. So with that, I'll move directly to Michael to go into the RSQKit.
Hello. So I'm Michael Sparks. I work at the University of Manchester, and I am one of the editorial board members for RSQKit. I'm also part of the Escape cluster as part of Work Package 4, so one of the pilots. So if we move on to the next slide, what is RSQKit? Well, RSQKit fundamentally, at the end of the day, is a website. Is one way of is the glib way of describing it. But in practical terms, what is it? It's essentially a place where somebody can go to figure out how to manage the development of their research software project. It's somewhere where somebody might say, I want to be able to point an early career researcher out here so I can figure out what the best practices are for me. So how do I use Git? How do I cite my software? The aim is to collect the timeless pieces of information that are useful when building out research software projects and in making sure the quality is sufficiently good to enable reproducibility, because reproducibility is the heart of science at the end of the day. There's also things like the social aspect of people wanting to have a handle on the research software quality and the backup practices that people are doing. We want people to be able to go away from this and have the confidence that they are addressing the research software quality topics that matter to them, and so they can support learning within their teams. So on that basis, that's where the various different pieces come into play. So we have essentially the conceptual model, which has been loosely talked about, the tiers model, which Fotis mentioned. We've got the concept of things like quality in motion. So quality in motion is projects which are active. They have a current state of play. You can capture that state of play, and we call that a research software story. Describes the quality practices that somebody uses. It describes the tools and the lessons they've learned. It also is a moment of reflection and introspection when somebody creates one of these things, because it helps them identify gaps and holes as to where they might want to improve their own research software quality in their project. And so this is valid for a project that's 6 months old and very, very new and nascent, through to a project that's 20 years old. And we do have project descriptions of spanning both of those sorts of levels of depth. And the reason for it is somebody can come to this and say, what did they do? Who's like me, and what did they do? And so once you have that, lots of the other things fall out. So the roles and responsibilities aspects about what people what somebody knowing, what does someone like me need to know? What can this give me? What tasks can I take away from this to learn? So that's where the quality practices come in. The quality practices are generally captured in task pages, and the task pages is where the bulk of the information is at the moment. And this is the things like, this is how you use Git. This is what version control is, which is not actually necessarily the same thing. One is a tool, one's a practice. This is aspects. So there's aspects around tools, there's aspects around guidance, there's links to training, and so on and so forth. And the key thing is that this is an open platform. So we want people to get involved, and we want to be welcoming to your ideas. We want you to challenge our ideas. We want you to share our ideas. And the idea is that we'll improve And we won't reinvent, but we link out to the best practices and we support the community. One of the best descriptions I've heard is this is a get fit guide, not a how to build a better human guide. So if we move to the next slide. This essentially is just a snapshot of the usage for over a 6-week period, over a relatively quiet period, over the Christmas period, largely, but also January and leading on to early February. And you can see there's quite a lot of different areas of the world which are using it, and we'd like it to be more widely used beyond those areas. The areas which aren't as blue, we would like to be bluer, fundamentally, so we have more engagement. And engagement is the phrase. I don't want views. I want engagement is where people look at what we're doing, they feedback, and the whole resource improves. So if we move to the next slide, talking about engagement, the things you can do is you can look at the task pages, you can look at the research software stories, and you can look at things like and you can add reviews and you add comments onto the GitHub repository, because all of this is done using GitHub. So this is all available for you to contribute that way. You can also share back tasks that you think we should be having, your roles, your infrastructure, which is going to be different from ours. There may be overlaps, but there will be differences. Resources, tools, and your research software stories. That's the bit that people really learn from. What are people like me doing? And how can I improve? And how can we share our best practices between our projects? And so if you want to get involved, the final slide is of who the editorial board is. I'm just one of a team of many, and we meet once a week, and we hope to be very welcoming to you and hope to see you and hope you're willing to join us. And if failing that, I hope the RSQKit is useful to you. So at that, I'll pass over to Danny, I believe.
Yeah, thank you, Michael. So, well, following up, my name is Daniel Garijo. I'm from the Ontology Engineering Group at the Universidad Politécnica de Madrid, and also one of the partners of the project. As Michael said, I'm also part of the RSQKit editorial board. And today I'm gonna be talking a little bit about software quality and how we measure indicators and assessment workflows within the EVERSE project. So the next slide, please. Thank you. So the thing about software quality is that a lot of work has already been done, right? And if you look a little bit over the web, you'll see that there are already quality standards like the ISO IEC 25010, which defines the different categories for software quality, such as, I don't know, documentation, maintainability, and so on. You will also find many best practices by different communities like CHAOS or RSMD that define metrics that may be used as reference to, measure against your research software. And finally, you also have tools like OpenSSF, CFE-Convert, or Heusden that will perform quality checks that will assess a certain part of a given set of metrics that probably that community has also defined or considered important. So the first question that we have is like, okay, given all this landscape, how do we bring everything together in a single quality framework that actually help researchers assess also their fairness, which is one of the quality aspects that we were very interested in. Next slide, please. And in the end, what we have done is try to do a very simple but effective quality framework, which introduces three main concepts. One is the notion of a quality dimension, which is like a general criteria, a general category for grouping more granular indicators that measure some aspect of software quality. Then you have the indicators themselves, which are the metrics, and indicate something in particular that can be measured about a given software repository, right? For example, test coverage, documentation coverage, etc. And finally, we have the quality checks that different tools that already exist, because we don't want to reinvent the tools, that different communities have put together measure regarding these quality indicators that also different communities have already done. So an example can be seen on the right, where you have a general dimension, which can be considered fairness in general, right? Fairness for the research, the FAIR principles that Fotis was referring in his introduction. And then you have something like an indicator that can be, well, one of the specific things that fairness measures, such as software has a license. And then you have the specific quality check that a particular tool does, because even something so simple like software has a license may be interpreted in different ways, such as, well, is there a license file, or the code has a license, or someone has put it in the GitHub API through a direct annotation in the website, right? Next slide, please. So what we have done is that we have grouped a catalog of research quality indicators that come from the state of the art. Right now, I think we have like around a little more than 30 indicators, 34 indicators organized in different quality dimensions. Most of them come from existing standards. And the rest of them, the indicators themselves, we have, again, not defined them ourselves. Most of them come from good practices, existing EOS projects, existing tools that measure that aspect, or that have considered that that aspect of software is important, right? This is maintained in a GitHub repository. It's in the EVERSE organization, and it's open for contributions as well. Next slide, please. So, as I was saying, the catalog not only brings the indicators, but also does a mapping between what the different communities have considered important. So in this table that you can browse in the URL in the slide, you can see how different communities have considered that, for example, it's important to have a static analysis tool for common workflows assigned in a GitHub repository, no? And each of the columns indicate the different communities that we have investigated and incorporated into the comparison side by side. Of course, having a full, complete picture is often quite challenging. So if you see that there are other communities that we may have missed, please let us know and open an issue. Next slide, please. Another thing that we have done is because there are several clusters included as part of the project, is that, well, each of these communities themselves have different requirements for the different maturity levels of the research software. Fotis was referring to analysis code. There are 3 different levels: analysis code, prototype tools, and research software infrastructure, and each of them may have different requirements according to these communities, right? So what we have attempted to do is also start categorizing how important are each of these indicators for each of the maturity levels of the research software. Next slide, please. And in the end, these indicators are a little bit of the backbone that powers the whole project, no? Because the indicators are referred to the best practices in the RSQKit, just described by Michael. Then they are associated with measuring tools or tools that can be used to improve them in the TechRadar that will come later. They are used to power up the quality pipelines that I'm going to describe in a second, the research assessment workflows, and they can be visualized in the dashboards that Faruk is going to present in a second. But the indicators are like in the middle because they connect all these tools as some sort of also of interoperability framework. Next slide, please. So coming up to the second part, which are the research assessment workflows, we have tried to make this as easy as possible to adopt. So we have 4 main steps to adopt them. The first thing that you have to do is to sit down with your community and think about which indicators you would like to consider for your particular community, no? Because not all communities may agree. And we have done some default values, but maybe you don't agree with us, and that's completely fine. So the first conversation that anyone aiming to adopt this framework should have is just sitting down and see what is the list of things that we think it's important to have for our domain. Then we have a tool that is called RSQKit for the research software quality pipelines. And you can install it or place it as an action in your GitHub repository, configure it with the indicators that you have selected, run it, and then browse the results. So very simple 4 steps. Next slide, please. I wanted here to illustrate how this would look in practice, right? In practice, you set up the indicators you want to run in a configuration file. So for example, let's say that I think that having a license is crucial, that it's very important to have a citation and to have continuous integration tests as part of all the repositories in my organization. So then I would select these indicators. I would select the repository or repositories where I would like to run this. And then this would be a GitHub action. Basically, every time you want to do a major commit or release, you will see that this is running, and it would tell you a report like the one that you can see here, like, hey, okay, well, I see that it has a license. I see that the citation is missing, and so on, so forth. Also, a summary in a machine-readable way is produced, which is the one on the right. This is a JSON LD, which is basically a JSON file, so it can be propagated, for example, through visualization dashboards, which is what is going to come next by Faruk. And with that, I forward the presentation to you, Faruk. Thank you.
Thank you, Daniel. My name is Faruk Diblen. I'm from the Netherlands eScience Center, and today I'll be talking about Dashverse, which is a dashboard for EVERSE project. Next slide, please. So it's essentially a dashboard with interactive charts, visualizations, and specifically designed for EVERSE project so that we can use existing schemas, indicators, dimensions, and we can visualize them interactively. And Dashverse is providing some pre-made charts so that you can interactively play with them. But also it's possible to have other type of interactions via your custom-made code or service, etc. And the entire platform is fully deployable either locally or on a cloud. And the deployment itself is fully automated with scripts and the tools coming with Dashverse itself. And you can also fully customize all the dashboards, all the charts of Dashverse. The code is stored on GitHub. You can just have a look, and you can, yeah, the link is at the bottom. So it's fully open source. You can just have a look, and you can also try to install it yourself. Next slide, please. This is basically very high level overview of software stack. So we use Kubernetes under the hood to make things scalable, and also you can have multiple nodes with using Kubernetes so that you can combine different sources. The orchestration, basically deployment, is made by Terraform, Ansible, Kubernetes. These are the technologies we use to deploy the entire stack. There is a typical relational database, PostgreSQL. We have an API layer. This is yet another service so that you can use this API level abstraction to talk to the dashboards. And under the hood, there is an analytics platform called Apache Superset. This is basically what makes everything interactive on the front end. And then we also have authentication server that is allowing users to push some new data to dashboards. Next slide, please. In EVERSE project, we identified 5 roles, 5 different roles: policymaker, principal investigator, RSEs, researchers who code, and also trainers. So those 5 roles are also reflected on Dashverse. We have a demo portal just to show how it looks like. You can basically go to this website and then you'll see running a demo. That's not meant for production, but this is just to show how the system is and what you can do with it. In those 5 roles, there are a lot of charts and data views tailored to use the indicators coming from the assessments from the pipelines. Next slide, please. So one of the use cases, this is a typical use case. You can run the pipelines that Daniel mentioned that will generate an assessment report, and then this assessment report can be fed into Dashverse, so you can read, you can see the results of the assessment. And next slide, please. As I mentioned, we also have an API. You can just go to this link to see online documentation of the API. You can use this API to basically change all the charts, all the dashboard data programmatically. So you can just change the charts, you can change the data, but you can also integrate it with your own services and CLIs or custom-made applications. And one of the, as I mentioned, one of the use cases we focus on is integrating this with the EVERSE quality pipelines, so that you can simply assess your software and push all the assessment results to dashboards and visually see where you need to do improvements. Next slide, please. As I said, there is also analytics interface. This is Apache Superset. If you're not happy with the pre-configured charts and dashboards, you can fully customize all the charts, all the dashboards, and you can add new charts, you can remove the charts yourself. So you can make custom dashboards if you have different needs, if you have different metrics to visualize. So you can have your own customized dashboards for your institution, for example. Next slide, please. Currently, Dashverse is fully functional, but we still need to do some improvements. There are some small tasks to polish charts and dashboards. We are also adding some extra filters so that you can easily play with the interactive charts. We also would like to get community support so that we know what kind of charts, what kind of dashboards we would like to have in the final product. And until the end of the project, I think we'll be actively getting feedback from community. Next slide. So this is where you can help. Please go ahead and try it out on the demo portal. You can just have a look at the dashboards, all the charts. You can provide feedback. You can provide feedback about usability or the metrics you would like to see, especially looking at those 5 roles and assessing whether this is actually what you want to see is quite important for us. And if your community needs different type of metrics, if you need different type of metrics in your work, I think we would like to hear this so that we can also optimize those dashboards. There is a beta testers group. You can also join us and become one of the beta testers so that you can actively provide feedback. And if you would like to make code contributions or code reviews, please do so. Everything is online on GitHub, and I'll be happy to hear your questions if you have any. And to the TechRadar now. Thank you.
I think I'm next. Hello, everyone. So I hope you hear me well. I'm Thomas Guillaume. I'm a member of EVERSE, actually leader of the work package on tools and services. And today I will tell you about the TechRadar. Next, please. So the EVERSE TechRadar is a catalog of tools and services that are designed to assess, measure, and improve the quality of research software. So some of them you know very well. Think about PyTest, think about Black, things like that, tools that can be used on software to improve or measure the quality. This catalog actually comes as an interactive website. You have the URL here, where you will find this radar, where we divide and classify the tools under their quality dimension that Daniel talked about, as well as the card grid that you see on the left, where you will find all the tools and where you can actually browse the catalog. Okay, next one, please. So with this grid, you can search and filter based on metadata that we have defined to find the right tool for your job and discover new tools. So you can search with free text, but also filter on this metadata. So for example, on the license, on the language of your software you want to apply the tool to, things like that. Okay, next one. And once you click on one of the tool card, you will have a complete description of the tool, its quality dimension, also the indicators it can improve or measure, the same ones that Daniel mentioned before, its license usage, and the classification we use also in EVERSE. And in addition, it will also suggest some related tools that you see here at the bottom. Okay, next one. So for the catalog, each tool go through curation. We have this list of criteria that we use to select the tools and services. So it should be designed to measure or improve the software quality. It should be used frequently on research software and should be actively maintained. It should adhere to the relevant research community standards and best practices. And it should have the capabilities to actually either measure, analyze, or improve the software quality across the research software lifecycle. And so new submitted tools are reviewed by our curation team. And actually, next slide, I will talk about that. So the catalog itself is implemented as a set of JSON files following a defined schema in our GitHub repository. So this is an example for one tool, if you know JSON. So where we define all these metadata that we have seen in the display. Next one. And so you can actually contribute, and you are very much invited to do so, to the TechRadar, to add new tools or to keep them up to date if you see something wrong in the tool description or metadata. So you can do that either through a form that is accessible through the website with a suggest a new tool button, or directly edit the JSON file and do a pull request to our repository. And this pull request will go through the curation that I mentioned, and then be integrated into the catalog. You can also contribute in other ways. Technical contribution are welcome to the user interface. You can report issues, of course, suggest some improvement, or just give general feedback. And you can as well join the curation team if you want to do that. You can see our contributing guidelines for more details. And yeah, this is a community effort, so don't hesitate